Now, we've had a chance to think a little bit about this. We can also think about other time intervals, right? Maybe I want to know what's happening between instant 1 and instant 9. So I could relabel this, let's say 1 to 9, and I would draw something like R9 minus R1, and again divided by T9 minus T1. And here what you can see is that you're going to have different position vectors. So if I go over here to my picture, I would want to draw an R9 vector like this, R9. And when I go to subtract these vectors, I'm going to redraw them over here, right? Here would be my big R1 vector. Here would be my R9 vector. It's probably a little bit less long than I've represented it here. That's pretty good. Again, I follow the rule here. I want to know what do I add to R1 to get to R9. So that would be a vector like this. So this would be delta R. Let's go ahead and label that 9, 1 here. And now what we can see is we get a very different displacement vector for delta R over here and for delta R over here. This one would be, 4, 1. And then I'm going to divide each of those by some amount of time. The good news is time here is a scalar, so it's not going to change the direction of those vectors. So I would expect to have a velocity vector, in this case, an average velocity vector that points a little bit up. And over here, my average velocity vector would point entirely horizontally, which sort of makes sense if you think about the motion of the ball. As long as I'm still on the flat part of the table, I'm going to only have average velocities that point sort of straight to the right, which is the direction the ball is moving. But once it has climbed up the ramp a little bit, it makes sense that the average velocity would in fact be a little bit tilted up.